41 trillion kilometers. That number, written out in full, would stretch across an entire line of this screen and still fall short of conveying the reality it represents, because it describes the smallest possible distance between us and any other star in the universe. The star closest to our Sun is called Proxima Centauri. It belongs to the triple star system Alpha Centauri and sits exactly 4.24 light-years from here. Stated like that, it almost sounds reasonable. It even sounds close, especially when you remember that the observable universe spans 93 billion light-years in diameter. But that apparent closeness is an illusion conjured by the staggering scale of the cosmos. And truly understanding what those 4.24 light-years mean is one of the most unsettling and yet most fascinating mental exercises that astronomy can offer anyone willing to stop and think about what they are actually seeing when they turn their eyes toward the night sky. When you look up at the night sky and find that faint point of light that is Proxima Centauri, your first instinct is to feel it as something distant, yet perhaps reachable, like a lantern hanging high on a mountainside. The reality is something else entirely. What your eyes receive in that moment is a photon that left the star more than 4 years ago. Not a live image. Not a real-time transmission. Not even close. A portrait built from light that spent 4 years and several months crossing the absolute vacuum of space before finally meeting the retina of your eye at this exact instant. The star you are looking at is not the star as it exists right now. It is the star as it was when you were 4 years younger than you are today. If Proxima Centauri vanished completely at this very moment, you would still see it blazing in the sky. For 4 full years, with no way of knowing it, had disappeared forever. And that is only the distance expressed in travel time for light. And light already moves faster than anything else in the universe. When you begin converting that distance into kilometers, the number shatters every perception you ever had about what it truly means to be far from something. A single light year equals approximately 9.46 trillion kilometers. The distance light travels in 1 full year, moving at 299,792 kilometers per second, a speed no known mass in the universe can even begin to approach. Multiply that figure by 4.24 and you arrive at roughly 40.1 trillion kilometers. For a reference, the human mind can actually hold. The distance from Earth to the Sun is approximately 150 million kilometers. Proxima Centauri is 267,000 times that distance from us. 267,000 times the distance between you and the star that warms your face every morning. That comparison begins to warp perception in a productive way, but it still does not fully capture the reality. So try another scale, one that can be physically visualized. If you shrank the sun down to the size of an orange and placed it on a table, the Earth would be a grain of sand orbiting just over 10 meters away. At that reduced scale, where an entire solar system would fit inside a generous room, Proxima Centauri would be more than 2,700 kilometers from that table, not 2,700 meters. Not 2,700 city blocks, 2,700 real kilometers, roughly the distance from Sao Paulo to Belém, crossing half an entire continent, and all the space between that orange on the table and that imagined star in Belém would be completely, absolutely empty. No drifting rocks, no visible dust, only the cold, silent, unimaginable vacuum of interstellar space, stretching in every direction, offering no stops, no waypoints, no points of reference whatsoever. What this scale reveals is something most people never truly stop to absorb. The stars that scatter across our night sky are not close companions to Earth. They are neighbors divided by chasms of vacuum that defy every attempt at intuitive understanding. The starlit sky, which appears so full, so dense, so saturated with light, is in reality almost entirely empty space. Every brilliant point of light you see is a distant sun, some larger than our own, some smaller, some older than the solar system itself. All of them separated by voids that render the distances between cities, countries, and continents completely insignificant by comparison. Proxima Centauri is the closest of them all in the known universe, and even so, the distance that separates us from it demands a complete redefinition of what the word far truly means. The sheer scale of that void carries consequences far beyond philosophy or poetry. It defines what is possible for a civilization that dares to aspire to one day reach another star. It establishes the boundaries of what physics permits and what engineering would need to overcome. And it begins to reveal a profound truth about our place in the cosmos. We are not isolated for lack of stellar companions. We are isolated by the geometry of the universe itself, a geometry that has constructed the space between stars with such boundless generosity of vacuum that no human mind can visualize it without reaching for metaphor. And the question that this void poses is not merely philosophical. It is the most practical question humanity can ask about its own future. What would it take to cross it? If humanity decided today to send a probe toward Proxima Centauri, what would be the very first thing engineers would need to calculate? The maximum speed that current technology can achieve. And that number, when it finally appears, completely transforms the conversation about what it means to be separated from another star by 4.24 light-years. The New Horizons probe, launched in January 2006 with the primary mission of studying Pluto and the outer reaches of the solar system, is one of the fastest objects humanity has ever hurled into space. It travels at approximately 58,000 kilometers per hour, a speed that by any human scale of reference is nothing short of extraordinary. At that speed, New Horizons would take approximately 73,000 years to reach Proxima Centauri. 73,000 years. That was when the first anatomically modern humans were leaving Africa and beginning to spread across the planet. And even then, the probe would still not have arrived at the nearest star. To make that scale even more concrete, in 73,000 years, entire civilizations would have risen, flourished, and vanished dozens of times over. The Portuguese language you are hearing right now would no longer exist. No language spoken today would survive in any recognizable form. The pyramids of Egypt are roughly 4,500 years old, and already we regard them as relics of a distant antiquity. The full journey to Proxima Centauri with our current technology would take the equivalent of more than 16 Egyptian civilizations stacked one upon another. And even at the end of that astronomical wait, the probe would arrive with no human being on board, no ability to return, and no way to transmit data back in any useful time, because radio communication also travels at the speed of light, and would itself take another 4.24 years just for the arrival signal to reach us. So what about Voyager? Voyager 1, the most distant object humanity has ever sent into space, was launched in September 1977 and is still traveling. It moves at roughly 61,000 kilometers per hour, and over nearly 5 decades of unbroken journey, it has covered more than 24 billion kilometers. A distance that sounds immense until you remember that Proxima Centauri lies 40.1 trillion kilometers from here. In other words, after nearly 50 years of continuous travel through space, Voyager 1 has covered less than 0.06% of the distance to the nearest star. If it continued in the same direction at the same speed, it would take tens of thousands of years to arrive. It will never arrive. Not on this trajectory, not with this technology. Humanity will exist in forms we cannot even begin to imagine before that probe ever crosses the full breadth of interstellar space toward our neighboring star. What these numbers reveal is not cause for despair. They are cause for understanding the true scale of the challenge. The physics is unambiguous about what separates our current technology from what any practical journey to another star would actually demand. Even traveling at 10% the speed of light, a velocity that would demand an amount of energy equivalent to all of humanity's electrical consumption across several centuries, the journey to Proxima Centauri would still take more than 40 years of continuous travel. At 20% the speed of light, that time would fall to just over 20 years. But no existing technology can even remotely approach those speeds with any object of meaningful size. The barrier is not one of will or creativity. It is one of physics and energy. Light itself, the ultimate speed limit that known physics imposes on any object with mass, would still take exactly 4.24 years to cross that distance. This is not an engineering problem that can be solved simply with more funding or incremental innovation within what we already know. It is a barrier set by the very fabric of the universe, and it makes every star you see in the night sky not merely distant, but separated by a kind of distance that defies any analogy to human experience of travel. When you look toward Proxima Centauri and imagine journeying there, you are contemplating a voyage that would consume the entire recorded history of human civilization just to begin, using the means available to us today. That is the true weight of 4.24 light-years, measured not in kilometers, but in human time, in generations, in everything civilization has built and lost, while those stars continued burning, indifferent in the sky above. The distance is not a number. It is a declaration about where we stand in the universe, and about how much of our creativity has yet to be unleashed before that declaration can ever begin to change. And that is precisely why what lies between here and there deserves to be understood with care, because crossing that space begins with truly comprehending what it is. There is a question that almost never arises in conversations about interstellar distances, yet it completely transforms how you visualize the space between us and Proxima Centauri. What exactly lies between here and there? Most people's instinctive answer is nothing. And that answer is wrong in a very interesting way. Interstellar space is not the absolute vacuum that intuition imagines. It is permeated by something called the interstellar medium, an extraordinarily sparse mixture of gas, dust, and charged particles that fills the entire galaxy, invisibly, in every direction. The density of this material is inconceivable on any human scale. On average, the interstellar medium contains approximately 1 hydrogen atom per cubic centimeter. A single cubic centimeter, the size of a small sugar cube, contains on average just 1 atom. Compare that to the air you are breathing right now, which holds roughly 27 quintillion molecules in that same volume. Interstellar space is, in truth, extraordinarily empty, yet that near-perfect void is anything but inert. It is threaded by galactic magnetic fields that stretch for thousands of light-years in every direction. It is continuously bathed by cosmic rays, subatomic particles accelerated to velocities approaching the speed of light by violent events such as supernova explosions, neutron-star collisions, and magnetic jets launched by supermassive black holes. These particles travel through the interstellar medium in every direction, including through the solar system, through Earth's atmosphere, and through your own body at this very moment. On average, dozens of cosmic particles pierce every square centimeter of your body every second, and you feel absolutely nothing. The space between here and Proxima Centauri is not an inert tunnel waiting to be crossed. It is a dynamic, magnetized environment saturated with radiation, one that any interstellar vessel would be forced to confront across years or decades of unrelenting travel. There is also a precise physical boundary that marks exactly where our solar system ends and true interstellar space begins. That boundary is called the heliopause. Beyond it, the solar wind, the constant stream of charged particles pouring outward from the sun in all directions, no longer possesses enough force to push back against the particles of the interstellar medium. The heliopause lies approximately 120 astronomical units from the sun, equivalent to roughly 18 billion kilometers. In August 2012, after nearly 35 years of uninterrupted travel, Voyager 1 crossed that boundary and became the first object ever built by human hands to enter true interstellar space. It was a scientific moment of extraordinary importance. For the first time in history, a human instrument was transmitting data from within the region between the stars, a region that, until then, we had only ever studied from afar. What the measurements confirmed upon crossing the heliopause was a clear shift in the magnetic fields surrounding the probe and an abrupt surge in cosmic particle density, proving that the heliopause is a real, measurable physical boundary, not merely a theoretical line drawn on astronomical charts. But even after crossing it, Voyager 1 remains almost incomprehensibly far from Proxima Centauri. The heliopause lies only about 0.002 light-years from the Sun. Proxima Centauri is 4.24 light-years away. In other words, after crossing the boundary of our solar system, following nearly 5 decades of travel, Voyager 1 has completed less than 0.05% of the journey to the nearest star. Interstellar space is an expanse that stretches far beyond anything any probe ever launched has managed to explore. And what Voyager encountered at that boundary is only the beginning of what lies between here and there. The temperature of interstellar space varies in the most extreme ways imaginable. In what are known as cold molecular clouds, dense regions of gas and dust where new stars will eventually be born, temperatures can hover just a few degrees above absolute zero, equivalent to negative 273 degrees Celsius. In other regions, superheated by intense stellar radiation or by the remnants of stellar explosions, gas can reach temperatures of millions of degrees. Between here and Proxima Centauri, a hypothetical spacecraft would encounter these violent extremes throughout its journey and would also have to contend with the relentless impact of interstellar dust grains. At velocities representing a significant fraction of the speed of light, even a microscopic particle carries enough impact energy to destroy any material known to us. The space between us and Proxima Centauri is not simply an empty distance. It is a physical environment with concrete characteristics that make the crossing an engineering challenge of far greater complexity than the distance alone would suggest. Understanding what lies between here and there, the near-perfect vacuum, the galactic magnetic field, the cosmic rays, the heliopause boundary, the temperature extremes, and the interstellar dust, Amdeitan, is the first step toward taking seriously the idea of crossing that space. Because an interstellar journey is not merely a matter of traveling from one point to another in a straight line. It is a matter of surviving what exists between those points during a voyage lasting decades or centuries. And it is precisely because that space is what it is, vast, dynamic, radiative, and almost incomprehensibly empty, that the real proposals for crossing it are as fascinating as they are daunting. And yet, despite everything's smality, the impossible distance, the travel times that dwarf the entirety of recorded human history, the interstellar environment that defies every technology we possess today, humanity has never stopped dreaming of how to cross that abyss. And the most astonishing thing is not merely that these ideas exist, but that some of them are physically plausible, grounded in what physics has already established as possible. In 2016, an initiative called Breakthrough Starshot was publicly announced with a bold and sweeping ambition to develop and launch nanoprobes toward Proxima Centauri within a matter of decades. The central idea is physically elegant in its conception. Tiny probes, the size of a computer chip, weighing only a few grams, would be fitted with ultra-thin, highly reflective sails. A high-powered laser, built here on Earth, would fire a concentrated pulse of light directly against those sails. For just a few minutes, the accumulated pressure of light delivered during that brief impulse would be sufficient, in theory, to accelerate the probes to approximately 20% of the speed of light. 20% of the speed of light. That number changes everything about how we talk about interstellar distances. At that velocity, the nanoprobes would take approximately 20 to 21 years to reach Proxima Centauri, with a journey entirely within the lifetime of a single generation. 20 years of travel to the nearest star instead of 73,000. The difference is not one of degree, it is one of kind. But that number conceals a staggering list of technical challenges that reveal exactly what it means to attempt something never before accomplished in the entire history of engineering. The laser required to accelerate the sails would need to operate at tens to hundreds of gigawatts of power, an amount of energy that would demand a technological infrastructure that does not yet exist anywhere on this planet. The sail itself would have to be constructed from a material that reflects light with near-perfect efficiency, while simultaneously withstanding the intense heat generated by the laser during that initial burst of acceleration. Over the course of that 20-year journey, each nanoprobe would have to survive the impact of interstellar dust particles, bolt striking at a significant fraction of the speed of light. Collisions that, at such velocities, carry an impact energy far greater than the microscopic size of those particles would ever suggest. Upon reaching the Proxima Centauri system, the probes would have no way to slow down. They would simply streak through the system at tremendous speed, capturing photographs and collecting data during the brief window in which they passed close by, then transmitting everything back to Earth. That transmission, traveling at the speed of light, would reach Earth another 4.24 years later. In total, from the moment the laser fires to the moment the first scientific data from Proxima Centauri is received, approximately 25 to 26 years would pass. A project that begins today could deliver results within the working lifetime of the people building it right now. The question of why Proxima Centauri would be such a valuable destination has an answer that makes all of this feel even more tangible. In 2016, the analysis of astronomical data confirmed the existence of a planet orbiting Proxima Centauri, designated Proxima Centauri b. This planet carries an estimated mass of at least 1.07 times that of Earth, completes one orbit every 11.2 Earth days, and resides within its star's habitable zone. That band of distances where surface temperatures could, under the right conditions, allow liquid water to exist. This planet is real. It is confirmed by observational data. It orbits the closest star to us in the entire universe. And while there is no confirmed atmosphere, no confirmed water, and certainly no indication of life, its very existence fundamentally changes the meaning of those 4.24 light-years that separate us from Proxima Centauri, because we now know there is something concrete waiting on the other side. There are other approaches that various groups of physicists and engineers have studied over the decades. Nuclear propulsion concepts, both fission and fusion, propose using nuclear reactions to generate thrust far beyond anything a chemical rocket could ever achieve. In theory, sufficiently advanced fusion engines could propel a spacecraft to several percent of the speed of light, compressing a journey of tens of thousands of years down to a matter of centuries. There is also the concept of so-called generation ships, vast and self-sufficient vessels, inhabited by multiple generations of human beings across centuries of travel, with the descendants of the original crew ultimately arriving at the destination. This concept raises profound philosophical questions about what it truly means to send people on a journey from which they themselves will never return, trusting that their great-grandchildren and beyond will complete what they began. What all of these projects share is that they reveal something fundamental about the human species. When confronted with an obstacle that seems utterly insurmountable, The instinctive response is not resignation, it is imagination. The distance to Proxima Centauri is real. The vacuum is real. The laws of physics impose real limits, and yet there are engineers and physicists who dedicate entire lives to seriously thinking about how to cross that abyss, not as an exercise in science fiction, but as a concrete project. Perhaps what matters most is not whether these projects will succeed in the coming decades. What matters is what it says about us, that we keep trying to answer a question the universe posed when it created stars separated by trillions of kilometers of silent vacuum. There is a specific moment when the distance between us and Proxima Centauri ceases to be just a number and becomes something you feel. That moment arrives when you stop measuring that distance in kilometers or years of travel, and begin measuring it in terms of what it means for the concrete existence of every human being who ever lived upon this earth, all of civilization that arose on this planet, those who built Stonehenge, those who navigated the Pacific without modern instruments, those who raised the great medieval cathedrals, those who created writing systems more than 5,000 years ago. All of them looked toward that part of the sky, never knowing there was a star 4.24 light-years away. They never knew it had a planet. They never knew the star's name, the temperature of its surface, the mass of its body, or the orbits of the worlds circling around it. We know. We are the first generation in the entire history of life on this planet to possess that knowledge. And that is not a small detail. It is a shift in our position within the universe. The light leaving Proxima Centauri at this very moment will take 4.24 years to reach Earth. When it arrives, some of it will touch your eyes, or the eyes of whoever is alive in that moment, and it will appear to be nothing more than another star in the darkened sky. But you know now that that light made a journey of 40.1 trillion kilometers to reach you, that it crossed a void where there exists, on average, just a single hydrogen atom per cubic centimeter, that it passed through the boundary of the heliopause, entered interstellar space, traversed the dynamic emptiness between two stellar systems, and finally found its way to your world. Its atmosphere and its surface, before reaching your eyes. That light is not merely light, it is a message about the scale of the universe, and every person who gazes at the sky is the recipient of that message, whether they know it or not. The isolation that this distance creates is not an empty or somber isolation. It is an isolation that defines who we are and where we stand. We are a civilization on a rock orbiting a mid-sized star, separated from the nearest star by an abyss that our most advanced technology would take tens of thousands of years to cross. And yet, in spite of all that, we keep looking up. We keep building larger telescopes, sending faster probes, proposing lasers capable of accelerating chip-sized spacecraft to 20% the speed of light, imagining nuclear propulsion, designing generation ships. No species that did not care about the cosmos would do any of this. No species purely focused on immediate survival would bother calculating the exact distance to a neighboring star and proposing concrete ways to cross it. We do it because something within us recognizes that this distance, though immense, is not infinite. What this distance also reveals is that the universe was not built to be comfortable. It was built to be vast, immensely, disturbingly, wondrously vast. And the purpose of stars is not to serve as nearby destinations for a young species in a galaxy of 100 billion suns. The purpose of stars is to exist, to blaze, to forge elements within their cores, to die in explosions of inconceivable energy, and to scatter dust that one day becomes new planets, Mensihat, and perhaps new forms of life. We are, in a sense, that chemistry and physics confirm with precision, made from the remnants of stars that died before the sun ever existed. The iron atoms in your blood, the calcium in your bones, The oxygen you are breathing right now, all of it was forged inside stars that exploded billions of years ago. The distance between us and Proxima Centauri is real, but the connection between us and the stars is older and more intimate than any distance can erase. When you step outside and look up at the night sky, whether an hour from now or days from now, and you see those points of light scattered across the darkness, remember that each one is separated from you by an abyss like the one you now know, that the nearest star of all lies 40.1 trillion kilometers away, that the light you are seeing left its source years, decades, or centuries ago, that there is a confirmed planet orbiting the closest star to our own, and that you are part of a species that not only discovered all of this, but that is beginning, slowly, ambitiously, and stubbornly, to imagine real ways of going there. The universe built this abyss between the stars. Humanity is still deciding what to do with it. And while that decision remains unmade, we are already doing the most important thing any conscious species can do, staring into the abyss and asking, with deadly seriousness and without surrender, how to cross it. Do you believe humanity will one day bridge that gulf and reach Proxima Centauri? And in which generation do you think it will happen? Leave your answer in the comments, because this is one of the most profound questions our species can ask about its own future. If this documentary made the night sky look different to you, share it with someone who also deserves to feel the true scale of the universe. And if you haven't subscribed to this channel yet, do it now, because every video here is a journey to places very few dare to truly visit.